College Place is a video library of noteworthy presentations, panel discussions, and lectures featuring guest speakers and faculty members, taped at one of the Milwaukee Area Technical College's 4 southeastern Wisconsin campuses. These are produced by students in the college's Associate's Degree program in television video production in coordination with Milwaukee Public Television.
As Patricia indicated earlier, our second speaker this morning is the founding dean of the UWM Graduate Level School of Freshwater Sciences. He is an Australian, and we were able to bring him here, which we are delighted with. He is a specialist in water resources and pollution control and has been named this founding dean at UWM, and he started September 1st officially, although with our problems with the U.S. immigration, it was a little later than that, but they actually allowed him in the country. He comes to UWM from Environmental Biotechnology Cooperative Research Centre in Everleigh, New South Wales, Australia, where he had been executive director since 1996. That center brought together the multidisciplinary skills of researchers, engineers, and industry participants to discover novel technologies for environmental and other applications. The UWM School of Freshwater Sciences is the only graduate school in the nation dedicated solely to the study of freshwater issues. And David has had extensive experience in a variety of areas: management, technology, policy, and resource development, as well as resource management that will help bring together academia, public service, private industry here, as well as what he has done in Australia. So we're delighted to welcome David this morning.
Thanks, Sam. When I think about what you've already been presented with and the overviews, I feel a little bit as though I'm going to be preaching to the converted. You've seen a lot of the stuff. So what I want to try to do is to perhaps put a slightly different spin and show where the challenges are in terms of where things are going. So the basis thesis that I'm going to be talking about is to talk about the issues of water and water quality. And water quality is often neglected from the various aspects of generation. To look at some alternative and merging, and then finally to maybe take this: is there a line on the horizon? Is there hope or not? And what will actually drive that in terms of the world experience in water? This is a slightly different picture. So here we have the irrigation, we have urban development, we have freshwater ecosystems, and we have a typical view of power plants. And it is the interrelationship of those which this is really all about, and whether or not that changes. But the world is changing. And as we've already heard, these energy and water are inextricably interlinked. In slightly more detail, we can see that it's not just a simple circle. There is so much of it relates to large-scale production, comes down to small-scale operations, and the integration of those small-scale operations is the critical factor in terms of whether or not we actually need the large-scale production. But we need to challenge that. Do we need continuous large-scale production? And what is the basis for us for making those sorts of decisions? We've already been shown that the US freshwater consumption and how that divides up into the large amount in terms of irrigation. We've got domestic, commercial, thermoelectric, mining, and industrial. If we take that further and we look at the freshwater withdrawals, then we can see how those are divided up between the sectors, again, irrigation, industry and mining, and the thermoelectric. If we then put that into a much larger world context, we find that 80% of the world's future water stress is actually coming from population and development. At the moment, it is not coming from climate change. And you ask the question, in policy terms, are we looking at the right drivers? Because when much of the research is going into climate change, it doesn't mean to say we don't do climate change, but the immediate stress is in fact in population change, and that's a core underlying factor. So I'm not saying there's a right and a wrong. All I'm saying is we need to look at our drivers and to say it is people who are both the problem and, I believe, also the solution. And we have to appeal at a social level as much as we do at a technology level. Mike Lovell has just outlined how water availability is a nationwide problem in the US. In fact, all the water scarcity, based on that population growth, shows that it is occurring in water, all the population growth is occurring in water-short areas. And this is then beginning to give us an additional challenge. Is it enough of a challenge is the question we're asking ourselves. So already we've been told a little about water consumption and energy and how those things fit together. But you try and get some figures on this, they all differ. And the question is, why do they differ? Does it make any difference if they differ? And why and where do you come to that? If you do something called life cycle analysis, you'll find that the critical factor is where you draw your boundaries. And so you'll be presented, and whichever document you read, whether it's from the energy generators, whether it's from the environmentalists, or whether it's from academics, you must always ask your question, what are the boundaries which are being defined? Have they defined up front the boundary conditions of where they're drawing? Because if you draw slightly different boundary conditions, you'll get completely different answers. So 80% of, we're told in one paper that the US power use, thermal cooled water is 87% of the water. This amounts to nearly half a gallon per kilowatt hour of power used. Hydroelectricity, which is 9%, but the evaporation figures are not given. So those are, because of the boundary conditions which are drawn, they're zero, effectively. So they're not saying they're not zero, they're not saying they have a value, they're just saying, for our study, they're not given. And the renewables take about 4%. But again, which of those renewables did they include the section from the agricultural sector? No, it turns out, in terms of this, in this particular study. So we can then look at the various sources of power and then start looking in a bit more detail about how those come together. Now, let's just take an example of the Pacific Northwest region and in fact, electricity generation within the whole of the US. This is a graph of where hydroelectricity generation occurs within the US. And you can see that it occurs in places in a great deal, and most of those are the wettest areas. So you ask yourself the question, does it matter if because in the places where it's wettest, there's probably the least evaporation. We can go to other areas where there's a high evaporation rate, and the question we're asking ourselves, should we be using scarce water in those areas where there are high evaporation rates? I think in terms of an Australian context, this is like putting a hydroelectricity generation station in the middle of Australia, where 1/3 of the water evaporates each year, at least, and it doesn't matter how big a dam you built, you would never be able to use it in real terms. So it doesn't make sense in some cases to do some of these things. So we've again heard the figures. Do we look at the US population growing? So it's going to grow by 70 million in the next 25 years, so that electricity power generation should increase by 50%. Other aspects about it there are no changes. If we look at water consumption as such, the single factor which changed water consumption, the two factors are, one is pricing, full cost recovery. The second factor is social awareness. In Australia, we cut water consumption by half in some critical areas by an appeal to the community to, in fact, cut water by half. The whole program was called Better by Half. But the most thing, again, I'll come back to this, most of the growth is going to occur in areas of limited water availability, and so are we socially able to, in fact, to cope with this? Let's look at evaporation and generation. So here we got a completely different set of figures. And why? And we see that, in fact, that the evaporation per kilowatt hour at hydroelectricity plants, in fact, varies between something about 12 and 55 gallons per kilowatt hour. This is totally different from the 0 figure. And again, because of boundary conditions. So you actually need to look and investigate what it is. Overall, the figure which is used and often quoted in the US context is it is 2 gallons per kilowatt hour of site energy. But what is that's meaningless in terms of disaggregation, breaking it down as to where it's used and what's the significance of that water at that stage. So here we have the summary. 89% of the US electricity is from thermally driven. Evaporated and consumptive uses is about 2.5%. Hydroelectricity produce 9%. In thermoelectric plants, we got half a gallon, the figures. Hydroelectricity plants, as much as 18 gallons per kilowatt hour. And the average thermal and hydro water use is about the 2 gallons per kilowatt hour, which is, whichever way you look at it, is a lot of water, which means that if water is precious, that you are in fact using water, as has been said a few times here, as the future more precious than gold. So let's have a look and see how far we can go and what are the sorts of operations and where we go. Now, I've added to the energy and water cycle relationships some aspects of energy associated with water, also in terms of fuel production, extraction and refining, and then link that into the whole of the water and energy relationships. Here we have some really interesting figures in terms of which, if you're looking at large-scale generation, the simple thing with the lowest water consumption for an energy source is natural gas. So for large-scale production, the simple answer is we should be moving to natural gas. If we then move down, we find that, in fact, tar sands are really not quite as bad as water, but it depends on, again, boundary conditions. We start talking about LNG, and then we're actually moving up until finally we get into some the petroleum and, of course, the biodiesel figures. We're using very large amounts of it. Now, I want to take that just a little bit further. Let's look at fuel ethanol. So, depending on the source, you're using 32 to 10, just over 10 times as much, 370 litres per kilowatt hour of energy, depending on the source. But let's look at it in context. If it comes from Brazil, how critical is that? And yet, ethanol from Brazil is banned into the EU. How do we compete in terms of total water? If we are importing ethanol into the US, how do we look at it in terms of... And here we introduce this concept of virtual water. How much virtual water is in there? And the question is, do we think of it in terms of water trading? Are we able to grow the crops to produce the ethanol, which is quite often sugarcane based, in high rainfall areas which have natural high water, abundance, or are there other environmental aspects by which we say we shouldn't do it? On the other hand, we're weighing, should we be thinking in terms of what damage are we trying to do in trying to replicate that in areas where we don't actually have the water? So the concept of virtual water, water trading, and water trading on an international scale now becomes a new challenge. If this table shows that basically it comes back to the social aspects. That simple moderation of demand at a household level and at also an industrial level will make a larger difference to future energy demand more than almost any other single aspect. And so the question we'll be asking ourselves before we move to this, should we in fact do sociology training? Should we do communication? And how do we manage this in future? If we then look at some other areas, we can get multiple and complementary gains in both, not only in terms of reducing the amount of energy used, we also reduce the amount of water, and thereby, instead of moving from a vicious circle, we're actually moving into a virtual circle. And just about all of this is able to be done within your own, as individuals, your own power. And so we can show that production of drinking water and wastewater treatment, the energy aspects, we can do both the user side optimization, and we can also do both sides, the system and building those things, and rethink at the city level. So now we're thinking, okay, let's rethink how we deal with water and energy and that water-energy nexus. One of the things which is often, because of the coal-based or because of the way people look at it, is the aspects of power production. Where there's loss of habitat, we get intake areas, loss of fish eggs and larvae, and US EPA is doing a lot to look at that. There's a lot of dispute about all the various areas as well. And we can talk about the thermal impacts of discharges, both good and bad aspects. We can think about the cold water discharges from hydro. Whole populations of fish have been wiped out simply because having continuous discharge of cold water, when you need an increase, a very relatively small increase, to in fact to stimulate breeding, is a critical factor in terms of maintaining and stocking rivers. Sediment discharges have been a major problem, whether we move from China or even right through Australia and parts of the US. We're now reaching the stage of decommissioning of dams. These are big, big issues, and nobody has done it on a very large scale successfully, and yet these are an impact, and it's being watched very closely in terms of what is happening. And then there's the warm water from the cooling systems. And simply, there are just changes in water quality from the use. You're changing your actual net concentrations. Fuels as a source of pollution. Coals, typically, sulfur, particulates, mercury, and trace metals, dioxins, and ash leachates. Most of these are now, luckily, legacy problems, although as a legacy, we still have to deal with them. The big challenges are, how do we change the technologies to make that happen? So pulverized coal, which is now readily adopted around the world, is much, much cleaner. Clean coal, equivalent to natural gas, is a dream still. It still hasn't got there. And most water quality issues are generally being dealt with, but as we were reminded by our chairman, the big elephant in the room is carbon dioxide. And the question is, it's much more inefficient in terms of many of these systems, unless for coal-based things, rather going to natural gas. So water quality challenges add to the complexity. So we've got to have our traditional nutrients and micropollutants, and that is in fact exacerbated by the global water warming challenge. It is not a static target we're looking at. It is moving, it is getting more complex, and is going to become more complex as we go along. And basically, we have to do something about the legacy. So that is the picture of the future for global warming. So is it real? We know that we're collecting data. We've probably got another 10 years data before we can statistically say it is real. We do know the mechanisms. The question is, should we do something about it? So that's going to lead us to water shortages, flooding, water quality impacts, sea level rises, and lake falls. and it could include the Great Lakes as far as that goes, and increase competition for water. In Queensland, the water in their reservoirs for drinking water and for use for water cooling fell to 18% of their total storage. They'd had a drought for 5 or 6 years. They're in a high evaporation area. They had to spend money. One of the first things they did was to put in water reuse. This plant and the water reuse is actually run by Veolia, our next speaker, of course. But one of the things is they had an integrated water system, and one of the key things you'll see there is that water reuse, in fact, goes to the thermal power stations, which were in danger of actually being closed down because of lack of water. They committed something, I think that's transposed, but it's $4.6 billion to put in a complete integrated water cycle system, including desalination. What led to this, let's look at it, was a crisis. And the question is, do we have to always wait for a crisis before we start dealing with some of these issues? How close can we get to the last part of the the final hour before things go wrong? So let's look at new technologies. We have high-intensity solar systems. These are showing huge promise for large-scale generation, and a variety of different systems for doing that. We have new tri-stage gas and geothermal systems, photovoltaics, heat recovery systems, both household and commercial systems, fuel cells, which still need a little bit of a promise there, new battery systems, which are also being worked at UWM. So we talked about, I've mentioned the high-intensity solar, microbial fuel cells, which we've heard a little bit about, and which there's a lot of work going on, and carbon sequestration, which is still looking somewhat, shall I say, a little dodgy as to whether or not it's actually going to succeed. But the thing about doing that is restructuring our inputs, rethinking, integrating large, medium, and small-scale generation systems and multiple source generation. The outcome comes from that, if we start modelling that and optimising that, is we go to reduced water use, increased flexibility, and reduced carbon dioxide. So suddenly we're moving into the virtuous circle of being able to do this. So we go away from our traditional thinking, and then the question is we move into a social, local generation of some of these systems. And really, if you look at the exhibits out there, there is a lot of that can be done. So my conclusions are, it's likely that water availability will be a driver to accelerate change in the generation, in its location, in the technology being used, and it'll actually improve water use efficiency. And we've had enough examples around the world to say we know this to be true. Improvements in water use reduction will include overall reductions in energy consumption, and this is the sociological change. And the new technologies which are coming will lead to offset the amount of water quantity and water quality losses, but we actually require a rethink about how we implement those and the drivers for these to enable a rapid uptake. Thank you.
Dean Garman, and so I would like to attempt to answer it. You've said, global warming, is it real? I say emphatically yes. The 2000 climate scientists of the Intergovernmental Panel on Climate Change put the statistical certainty at 90%. A recent comprehensive worldwide survey indicated that 97% of the world's climate scientists consider it a serious problem and that it is anthropogenic. So my answer to is it real is an emphatic yes. And let me follow with this question. If energy and water are inextricably linked, I would suggest that climate and water are similarly inextricably connected. And I'll give 3 quick examples and then ask for your response. Number 1, evaporation. You emphasized the importance of that. Evaporation is increasing due to rising global temperatures. so that in the last 4 decades, the amount of water vapor in the atmosphere is 4% higher than it was previously. Secondly, sea levels rising. This is producing saltwater encroachment around the coastlines of the world, reducing the amount of fresh water that's available. And finally, the melting of glaciers worldwide is reducing potential freshwater supplies for much of the world's population. Now, one can always say that a hazard is defined by the risk to human beings, so that the presence of humans and increased population is always a major problem in any issue that affects human beings. But I suggest that climate change exacerbates the water challenges and that they are inextricably interrelated, and just as energy and water are, and that we shouldn't juxtapose them as competing, but rather as part of the same problem.
Well, I have actually very little to disagree with you there. I'm one of the scientists who believe that global warming is occurring. What we do not have is, in fact, what the impacts are all based on models. We do not have enough statistical data to prove that those models are in fact correct, and it's the meteorological models which are still waiting. We need the extra data to prove whether they're absolutely correct. It is not the fact whether the carbon dioxide levels are rising, whether or not there is some form of global warming. What I'm referring to was the fact the final impacts of that are still, to some extent, to some degree of dispute. I agree with all the other points, and in fact I mentioned all those points within my talk.
Could we just not have a debate?
And I believe that is the critical question which we have to come to.
Yeah, thank you. Let's move to our next question.
Yes, my name is Chris Cameron. It seems to me that there are some options for power plants, electric power, such as solar, photovoltaic, wind, that don't use water, dry cooling or hybrid cooling, which are a little less efficient but radically cut the water. But it's the biofuels as we go forward, as we increase our dependence, as at some point we will, where does the water from those come from? I'm wondering if that is the bigger challenge, and your thoughts on that.
As I said, that biofuels from the right source, from the right area, can in fact make a valuable contribution to this. I believe in the short term we will see a shift from agricultural products being produced for biofuels as the technologies come along. That will reduce, and that biofuels, except where they're being produced by non-water intensive basis, will in fact tend to be reduced, simply because the water is actually going to be diverted back to food production, because we're going to run short of food unless we get major efficiencies in the growth of food. So it is possible to produce good biofuels in areas which have plenty of water, and to use that in terms of this virtual water transfer into areas which actually have got low or which are water scarce.
We have time for one more question, and the young woman who's standing there, please, we need to keep on schedule. Thank you.
Hi, I'm Virginia with Milwaukee Area Technical College. I'd like to go back to what you said about natural gas using the least amount of water, so the production of natural gas being the most efficient when it comes to water. A lot of our natural gas there's a big push on for extracting natural gas via fracking. Fracking uses a ton of water and also contaminates the water that's in the ground as well as the water that's used to extract the natural gas. So how does that compute in your equation that says that natural gas is the most water efficient form of energy?
Okay, it depends on, again, let me come back. Let me define my boundary conditions and your boundary conditions. If you do it on the basis that natural gas, which is not produced by artificial, say from naturally occurring, most of that water is in fact recycled and can be treated and recycled. Does it pollute waters or groundwaters and other ones? The answer is it has done, and mainly the reasons for this is because of poor understanding of the areas or poor construction of the gas production lines. I believe there are guidelines, I'm not saying in all cases, but there are guidelines for both production, for recycling of water, and for treatment of that water, which will enable it to be very much more sustainable water. The figures which are used there for natural gas are for large natural gas wells, and so again, go back to your source, check where those figures come from, challenge me in terms of where those figures are. The figures have not been updated in terms of water used in fracking, but that's certainly an area where it needs to be done.
Thank you, Dave.
College Place is a video library of noteworthy presentations, panel discussions, and lectures featuring guest speakers and faculty members, taped at one of the Milwaukee Area Technical College's 4 southeastern Wisconsin campuses. These are produced by students in the college's Associate's Degree program in Television Video Production in coordination with Milwaukee Public Television.